Hi there, and welcome to the video about sheet 5 of the real numbers, the limits of sequences section of my course. The main item on the agenda today is tends to add. So why don't you see, we could do tends to neg, but we've done it before. So I'll tell you what I'll do. Let me do tends to, this lecture can be accelerated lecture style. So what I'll do is I'll start with tends to add and I'll go through it quite slowly, and then as the stream goes on, I'll introduce some more tips for people who want to speed things up. So how are we going to do this? I guess we've got to think about that. We've got to start by thinking about the maths. So tends to AT. What does this actually say? This says if AN tends to T and BN tends to U, then AN plus BN tends to T plus U. So the first thing we need to do is remind ourselves of the maths proof, right? What's the maths proof? What's the maths proof? The idea is eventually AN is within. Let me just pause this so it doesn't keep disappearing. There. Eventually AN is within epsilon over 2. This is the epsilon over 2 proof, the addition one, isn't it? Eventually AN is within epsilon over 2 of T, and eventually BN is within epsilon over 2 of U. There. And then we are done, right? And then done. So that's the argument. Now let's think about. I mean, I guess the first thing we should look at the limit, right? The definition. Sorry, the definition of tends to. Let's rewrite tends to def everywhere, so we can actually see. So we can actually see what the goal is. Let's start this up again. So there we go. So now, hypothesis HA says that for all positive epsilon, there's a bound such that if you're at least the bound, then you're within T of epsilon. And hypothesis B says there's an epsilon such that if you're greater than some bound that depends on epsilon, then Bn is within U. And we've got to prove that for all epsilon, there's a bound such that blah, 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 blah. So clearly the way to start is, the goal is we've got to prove something for all positive epsilon. So let's start, intros, epsilon, H epsilon. So now we have, that says, so what does that say? That says let epsilon positive be arbitrary. That's the first line of the proof. So now we want to use this. Eventually AN is within epsilon over 2 of T, right? So what is that? Epsilon over 2. You see, HA, the output of HA is a proof that that AN minus T is less than epsilon. So we want to run this function HA, but with the input not epsilon over 2, right? So let's specialize HA epsilon over 2. If I put epsilon divided by 2 like that, I should get an error. There we go. You see, I get an error because what happened is that HA is a function, so it's greedy. So it eats the epsilon immediately. It doesn't wait for the over 2. It just eats the epsilon. There you can see it says HA epsilon. It's eaten the epsilon. And now it's expecting a proof that epsilon's positive, but I've given it a division symbol. And the way to fix that is to put this in brackets. There. So now HA, we want to get out the fact that AN minus T is less than epsilon over 2, right? That's what we need. We need that something is smaller than epsilon over 2 and something else is smaller than epsilon over 2, and we're going to deduce that something else is smaller than epsilon. So we specialise A epsilon over 2, but now we need to prove HA, the next input that this function wants is a proof that epsilon over 2 is positive. So we can put an underscore there, if you like, and now look, we've got two goals. Because Lean is demanding a proof that epsilon over 2 is positive, but it knows the hypothesis that epsilon is positive. So you see we have two goals here, so I should do this to do it properly, and now we only have one goal. And how are we going to prove that goal? Well, this is just a sort of a linear, this is an inequality. I guess it is linear, even though I'm dividing by 2, it's still linear because 2 is a constant. If I had epsilon divided by delta, linearith wouldn't work. You see linearith Linearith works fine to solve that goal. You know, Lean's linear arithmetic tactics. So let's put bilinearith here. There. And now we can get rid of that line. You see, I'm just feeding the tactics straight in. I don't need to have two goals and then one goal. I use by because at this point we're not in tactic mode, and so by puts us back in tactic mode, so we can use a tactic. And what does that give us now? You see, eventually, what does this mean? Eventually, I should perhaps be. What does this really say? You know, it means there exists. What are we actually trying to do at this point? We're trying to come up with a bound, right? Where's this bound coming from? We need a bound such that if n is bigger than the bound, then an, you know, then an plus bn minus t plus u is less than epsilon. So where's this bound coming from? Well, you see, HA has given us a bound. HA says we have a bound such that beyond that bound, an minus t is less than epsilon over 2. So we want that bound, right? So the maths, let's make this maths proof a bit more precise, right? There's a bound. Let's give ourselves some more room over here. There's a bound, I don't know, x, such that if n is at least x, then an is within epsilon over 2 of t. And similarly here, right, there's a bound y, such that if n is at least y, then bn is within epsilon over 2 of u. There. And then we say we're done. So what do we mean by we're done? I guess we need to use, you know, we're trying to prove the existence of a bound such that something. So why don't we use the max of x and y, right? And then it should be easy. So that's what the maths proof is. And you see, we're not quite. We've specialised h. So now we can get the bound, right? So we could put this like this. We could put that there in a comment. So now HA is this hypothesis that there exists a B such that blah 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 blah. So now let's get it, right? So we could do cases HA with XHX. There we go. And there's our bound. There's our X. And there's the hypothesis that says for all numbers bigger than the bound, an minus t is less than epsilon over 2. Great. So that's what we want. And now we want to do this one as well. But specialize and then cases, I can do that in 2 lines, right? I can use obtain. So let me obtain the bound y hy, just to be, it would be hb epsilon over 2 by linearith. So that should be, I've just done those 2 lines in 1 line because, you know, I'd like to write short proofs. So now you see we have a bound y, and the hypothesis that if n is at least y, then bn minus u is less than epsilon over 2. There. And so now what's the next line of our maths proof? It's use the max of x and y. Okay, so let's use max x, y. There we go. And now what have we got to prove? Now let's go back over here. We've got to prove that for all n, if n is at least the max of x and y, then an plus bn minus t plus, yeah, something's less than epsilon. Okay, so let's let n be arbitrary. So now let's say n is at least the max of x and y. So that's intros n hn. Yeah. So now you see. So now we need to specialize, right? We need to specialize hx because hx is a function. It wants to eat a natural number n. A proof that natural number is at least x, and then it will give us the thing we want. And similarly, hy, it wants to eat a natural number n, and it wants to eat a proof that n is at least y, and then it will give us what we want. So let's specialize. What are we going to do here? We specialize hx at n, and then some proof, right? So I put an underscore for the proof, you see. So now we've got this extra goal, and you see the problem now. We want to prove that n's at least x. But what we have is that n is at least the max of x and y, which of course implies that n is at least x. But I mean, Lean is a dumb machine, right? Lean needs to be told. Lean needs to be told why that's true. And in the previous example sheet, I showed you how to work with that. I showed you what to do with with a hypothesis of the form max x y is less than or equal to n. We can rewrite what was it called? Max LE if, I think it was, at hn. there, you see. So this Hn used to be the hypothesis that n was at least the max of x and y, but using this lemma here that's in the it's in the library, max AB is less than or equal to C if and only if A is less than or equal to C and B is less than or equal to C. That's the form at which we want this. So now we know n is at least x and n is at least y. So now I guess we should do that there. And so now how do we fill in this underscore? Lee wants a proof that n is at least x, but that's just the first part of Hn. So we could probably do Hn.1. Great. And now you see we have this hypothesis. So now, great. Hx is finally what we want. Hx says an minus t is less than epsilon over 2. And similarly, I guess we want hy, right? So some specialize hy n, and that we want the second part of hn. And I'm slightly surprised that didn't work. Oh, because it's not called hy. It's called H capital Y. What have I done? Why did I do something foolish? Oh, I see. It was here. Let's go with H capital. Let's fix this up. This is going to go on the internet after all. There we go. And so now we are looking at a problem involving, now we are closer to Linnerith doing it. So right, yeah, then it's easy. We have to convince Lee that now it's easy. We're saying that an is within epsilon over 2 of t, bn is within epsilon over 2 of u, and therefore the sum is within epsilon of t plus u. So you might like to think that the Linnerith tactic would do this because it's very good at solving that kind of thing. But unfortunately, the Linnerith tactic doesn't know about absolute values. It's very good at solving even quite messy inequalities, but we need to rewrite this absolute value less than epsilon in a way that doesn't have absolute values in. And of course, absolute value of x is less than epsilon if and only if x is in between epsilon and minus epsilon. So that's going to be in the library, and indeed in the last video I showed you what that was called. That was called abs lt, I think. Rewrite abs lt, and let's rewrite it everywhere. So there we go. So now hx now says that an minus t is less than epsilon over 2 and bigger than minus epsilon over 2, and bn minus u is less than epsilon over 2 and bigger than minus. So you see now, we're in good shape, because now we might hope that Linnerith solves it now, but I think it probably won't. Yeah, it won't do it. Let me try this though. Does that do it? Yeah, there we go. So the reason Linnerith doesn't do it yet is because Linnerith doesn't know about ands in goals. Linnerith is like, actually, this isn't an inequality. It's two inequalities. But of course, what do you do with a goal which is an and? You do split. And now we have two goals, and the first goal is an inequality, and the second goal is an inequality. So Linnerith should solve the first one, and Linnerith should solve the second one. There. And in fact, we're in a situation where we did split, and then we did one tactic that solved both goals already. So you could do split semicolon Linnerith. That should do it. There we go. So that semicolon means do next tactic to all the goals produced by this tactic. So there is tends to add, and it's a theorem prover. We've done it from first principles. I know much shorter proofs of this using filters, but I'll talk about filters. I haven't introduced filters in the course yet. So I'll show you another proof of. I'll show you a two-line proof of this later on. But there's a 1, 2, 3, 4. Well, they could have been one line. There's a 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a 12-line proof. That's not ideal. And so now, but as I say, we'll fix it later when we've learned about filters. So now what's left on this course? You see, we've got two. There's two. We've got two levels of this computer game left. We've got tends to sub and tends to neg, and tends to sub will follow easily from tends to neg. So why don't we do that now? What's the idea? I get the point is, I'd like to use tends to add, and tends to add is talking about limits of sums of things. So it would be nice if I could rewrite the this difference as a sum, right? I guess, yeah, it would be nice if I could write x minus y as x plus negative y, right? So I want subtraction is addition of the negative. So that's called, what would that be called? Simp sub ec add neg. There, you see that's changed. That's changed both occurrences of the minus to addition of the negative. And so now I can probably apply tends to add. There. And there we go. Now I've got two goals. And the first goal, whatever does that first goal say? Let's cheer it up. There. The first goal just says tends to AT. It was using that lambda note. It's saying, yeah. Yeah, okay. Lambda n a n is just the function a, right? The function that sends n to a of n is rather more simply defined. That's just the function a. So that's what's going on there. So in fact, this tends to add. It wants two inputs, right? The reason apply tends to add doesn't solve the goal is that tends to add. You see, it wants. Yeah. See if I can catch it. There, got it. It wants two inputs. It wants the proof that an tends to t and the proof that bn tends to u, and then it will prove that an plus bn tends to t plus u. And we didn't give it any inputs, and so that's why we've got two goals. So in fact, the first input is just HA, so we could put HA there. And now we've only got one goal. You see, in this goal, we don't have, right? We want that, the second input it wants is that minus bn tends to minus u, but we've got that bn tends to u. But of course, that's exactly what tends to neg does. Tends to neg says if bn tends to u, then minus bn tends to minus u. So this should be exact tends to neg bn hb. There we go, and it is. So in fact, we could just put that there. We could make this as an exact, couldn't we? We could just put that there. We could change this to exact. There we go. So there's a two-line proof. As I say, I'm claiming that I know a two-line proof of this, but I'm not showing you because we don't know the machinery yet. So yeah, let's just go nuts. Let me show you some machinery. So there's a two-line proof of this, but in fact I think I can get it down to a one-line proof, because basically what we're saying is after you've run the simplifier, the goal is exactly something I can write down. So I should be able to use the simp there, using that. Does that work? There we go. There. So there's a one-line proof of tends to sub, but of course I'm assuming tends to neg, and tends to neg we're going to need some work, right? Tends to neg we're going to have to. I mean, I'm not going to do it like this again. Let's just try and do it quickly. What's going on? If I rewrite tends to def everywhere, let's just have a look here. You see this hypothesis. This hypothesis that an minus t is less than epsilon is extremely close to the goal, right? The goal is that the absolute value of minus an minus t is less than epsilon. So you can kind of see, yeah, you can kind of. The point is, I've got to prove that absolute. What do I need here? I need that the absolute value of an minus t is equal to the absolute value of minus an minus negative t. That's what we need. So let me just put that as a, let me make that hypothesis now. Have h, what was this? An minus t equals, it doesn't know what n is. You see there's a red underscore. So for all n minus t equals minus an. What was it? Minus an. I may as well just write exactly what it was. There's no point. Equals minus an minus t. There we go. That's the thing we're missing. So let me just sorry that for a minute. And now the goal is exactly the hypothesis HA modulo this hypothesis H. So maybe I could do simper H using HA. Does that do it? There. So that solved the goal modulo this kind of irritating thing. And the irritating thing is, so I guess intro n. I'm going to prove the absolute value of this is the absolute value of this. So, and this is, and in the last sheet I told you how to do this, right? I need to know that the absolute value of x minus y is the absolute value of y minus x. So let's read. What was that called? It was called abs is ab sub or something. Ab sub control space. Oh, ab sub com. That's what it was called. And now, you see, now these are equal, right? T minus n is equal to minus an minus minus t. So can I do ring nuf or something? Will that do it? No, how do I do it? So let me get rid of the absolute values. Congra primed 1, and now the ring tactical to it. So there we go. Oops. And that'll do. Could be shorter. Let me just leave it. This video's been long enough. So there's the proof of tends to add, tends to neg, and tends to sub.